Hello everybody, thank you for joining us today. My name's Amy Hodler. I am the program manager for analytics and AI at Neo4j. I'm here with my colleague Jake Graham, who is the product manager for artificial intelligence and analytics. And we're going to talk to you the next 40 minutes about how graphs enhance artificial intelligence, in particular about context. And we're also going to give you a few examples to walk away with. And so I like to start with a little bit of a level set around machine intelligence in general. And so there's a lot of different terms out there that you've probably heard: AI, machine learning, deep learning, a lot of different definitions. But at the really high level, what we're talking about are different ways to solve problems. In particular with AI, a way to solve problems and apply learning that mimics the way humans make decisions. And what we're really trying to do is develop probabilistic methods to use software to make predictions. Now, usually that's either to predict what comes next based on features or the information we might have at hand, or it's about predicting how to classify things. Am I looking at a cat or a dog? Should this community be classified this way or that? Are they similar or dissimilar to another community? Now, if we think about intelligence in general, and especially if we're trying to mimic the way humans make decisions, context is really important for that. It's really important for understanding. It's really important for predictions. Now, I have an example of doing that wrong, actually from my past. I'm developing a logistics solution for a company that shipped yogurt. We made the assumption that FOB, for a logistics solution, of course, would mean freight on board. It turned out for this company, FOB meant fruit on the bottom. And that was very significant to them. It meant for them that those yogurts needed to go in different containers, different shipping methods. And so our solution failed them. Even though we had done a very clever job, we'd done a lot of deduplication for that FOB classification, and we hadn't taken in the context of the current situation. We had only learned from our past. And if you think about how humans learn, we, in general, maybe not always, are pretty good about trying to understand from our past and then applying that in a variety of solutions, variety of different ways. And so if we think about how humans can do that and trying to mimic that, here's an example of how a child might learn to do something, or rather not do something. I don't know if you all know what's about to happen. I actually did this as a child. I burnt my hand on the stove. Now, what's remarkable, or maybe not remarkable, I didn't need to do it a second time. I didn't need to try another time. Now, an AI solution or machine learning solution might need to try 1,000 different times. Try the spot in the back, try the spot in the front, try it a different time of day. I didn't need to do that. I didn't need to try it again at my neighbor's stove. When we got a new stove, I didn't need to do it again because I had learned very quickly from this traumatic experience that anything at counter height that you cook on with metal that felt warm as you approached it was not something you put your hand on a second time. Now, if we want to do that with a machine learning type scenario right now, that can be very difficult if you don't provide thousands of different examples. So another example, taking this context idea a little further is, I've learned this as a child in this scenario with a stove. But another example, my father used to race motorcycles, and the pipes and exhaust on motorcycles can get very hot. Now, you would hope that I'm not gonna show you another traumatic event, because as a child, I had learned from the first event that something that I approach that's metal, that's warm, that I'm not going to touch again, that I'm not going to try this again. And taking that context from very specific to more general, to even more general, is that expansion is considered contextual learning. I don't need to have an exact same situation. I've learned by context to apply that what I can now recognize of that event. Now, we would like to get AI, machine learning, closer to that. Now, unfortunately, we're not quite there yet. There are some things we need to do. Now, it's probably pretty clear from the previous example that missing contextual information is a big deal. AI is very good at very specific, well-defined tasks, but it struggles sometimes with ambiguity, with missing information. Machine learning often doesn't use some of the most predictive elements that we know of, which are relationships, especially if those relationships are hard to reach or process. The other thing is that processes that we have are mired in these older layers of complexity. A lot of this math has been around for decades. We've done very good recently with optimizing some of the hardware, and Jake will talk about process optimization, but we haven't used context to optimize that higher level process overall. There's also a lot of missing context in knowledge systems. They're missing that adjacent information, getting the right data for the right decisions. If we think about the FOB example, the software worked just splendidly, but it was the right solution for the wrong problem. It wasn't appropriate for that situation. So the other area that is becoming more critical is explainability. So we often can't explain, especially when we're talking about deep learning, why or how a decision was made. And so without context, that can be really difficult. And that's an area Jake's going to talk a little more about as well, and how that can really help us move forward. So graphs enhance artificial intelligence by providing context. So if you take nothing away from this talk, take away the idea that adding in that rich layer of information that's all around us into your AI solutions so that you can have better AI outcomes. And so there are 4 different areas you heard about this morning that we're going to talk a little more about. And the first one is connected feature extraction. How do we get connected features? When we're talking about predictive features, how do we get those connections so we can have better accuracy?
We'll talk a little bit about graph accelerated machine learning, so model optimization, so you can have context for better efficiency. We'll talk about knowledge graphs as well, which I think there's a lot of information out there. This one I kind of get excited about. So it's context for decisions. And I always like to add appropriate decisions in decision support. So there's a difference between accuracy and appropriateness. It's good to have both when you can. And AI explainability, so that's bringing context for credibility. So we're going to dive into connected feature extraction first. There we go. And when you think about this, it's kind of fun. I mean, I always think about, sometimes it's who you know. So I think Hillary must have stole our example on this. So I'll give you a different example. So if you have a lot of relationships, the 2nd degree, 3rd degree relationships with people that perhaps have committed some kind of a crime, that's a better indicator of you potentially having a criminal activity than some simple demographic. So, very simply, I think with Hillary's description on the smoking, it's also been proven with other aspects as well that you wouldn't think would naturally correlate with relationships. Unfortunately, current machine learning methods use vectors, matrices, tensors that are pretty much built from tables. And I'm sure you've heard in other lectures the difficulties of tables displaying and holding up relationships with the multiple joins, especially as you try to add in more. And these methods pretty much try to abstract, simplify, and sometimes just completely leave out entirely these predictive relationships and network data.
I just wanted to point out one thing on the visual you're seeing. What you're looking at are not tensors, right? You're looking at tensor spaces. They're the spaces in which a tensor could occupy. You can have simple one-dimensional tensors that are basically vectors moving into multi-dimensional tensors. But I've got my phone up here. I wanted to make sure I get it exactly right. The Wikipedia definition of a tensor is a geometric object that describes linear relations between geometric vectors, scalars, and other tensors. I think the important thing to focus on there is linear relationships. Right? Vectors, tensors, matrices are good at showing one degree of relationship. But that's not the entirety of what a predictive relationship is, right? It doesn't take into account more complex networks. It doesn't take into account multiple hops of relationships, but those can be very predictive. And where a graph fits in is to help, one of the places, at least in lowest hanging fruit, is to help deliver those predictive relationships into your current tabular or tensor-based model.
Yeah, and you can do that without actually having to alter your model and your other algorithms that you're using as well. So adding those in without having to change what your pipeline might look like. And graphs also are pretty good at inferring relationships. So I'll talk about that in a moment, where relationships don't exist or are very sparse. By using those second, third degree hops, you can infer relationships even if they're distance that don't directly exist. So very good with that. And we have a couple different methods that you can use to do connected feature extraction. You can use engineered features. So those are looking at labels or inferred relationships where you know what you're looking for. I want to know how many, at 4 hops, how many people have a fraudulent account. And I want the count, and I need to abstract that and then use that in another way. Graph algorithms are really good at finding things where you kind of know what the structure is, but you don't know exactly what you're looking at. So an example would be, I want to find the node in my network that can reach every other node the fastest. So I know what the structure I'm looking for, but I am not sure exactly what the node attributes are. Another example would be influence. Centrality algorithms are used quite a bit, where you want to know the influence, but you don't know exactly what that's going to look like or what the node's going to look like once you find it. And then with graph embeddings, that's kind of all the way on the other side of being more unstructured on what you're looking for. In that case, you're taking all of the relationships of the nodes and trying to abstract them numerically and then use them in something like a tensor. Now, an example we're going to show is in a financial crime scenario, a fraud prevention scenario. And finance is a great area to look at because there is just so much data and is so highly related, and especially in kind of fraud or criminal scenarios when the attempt is actually to hide using multiple hops and multiple network relationships. So with this example, this is a very toy example. It's a very small example. We might have a couple of accounts. Of course, you have hundreds, thousands probably accounts. But somebody perhaps is looking to make some kind of application, a financial application, whatever that might be. And the immediate thing you'd want to do is, well, let's look at who they're connected to. And you can really quickly look with just these couple hops and start to see some interesting indicators, people using the same social security number, same phone number. That's kind of looking a little suspicious. And so at 2 hops, we can see 4 connections already that might be marked as fraudulent or potentially fraudulent. And if you go out just another hop, we've added 3 more 4-hop connections. So pretty simple. You can imagine you want to do this with a lot more features. You want to do this with a lot more attributes. But you can see very quickly how it would be easier to follow the hops and find your connections than to do a complete brute force. Now, this is kind of an interesting scenario. Once you've found this or you've identified this fraudulent potential network, you can then do further algorithms on it to look at, well, who is the biggest influence here? What features are the most influential in this? You could project out to a subgraph and then do some analysis on that. We have several customers that use PageRank actually to look at their models and try to figure out which feature is the most influential in their model. So they don't even care what the feature is itself. They're just within that, find me the most influential feature, and then those are the top 10 or whatever we'll look at, and we can disregard the other features.
And another thing that you can do is you move from investigation into a pipeline, right? The goal of data science in general is to understand the predictive relationships in the data and then move it into something autonomous. Really, we want to be able to detect these things before they happen. A simple example of an engineered feature in this case is simply running a count. At every connection, how many known money launderers are there, right? And in this case, what you might find is you're not connected to any known money launderers at 1 hop, but at 2 hops, there's multiple. And at 3 hops, you're seeing this pattern. And what you can do is engineer features to build into, be it a rules-based engine, be it a random forest, be it any other model, to look at how many known fraudulent accounts at 1 hop, at 2 hops, at 3 hops. And those tend to be highly predictive features that are close to impossible to get out of any tabular data structure.
Great. And then what we can also just quickly take a look at is the machine learning graph algorithms. So you can see last year we debuted our graph algorithms library, had all of, had your standard graph algorithms areas, and then this year we've also just about doubled in size in algorithms. Pathfinding search, all about finding optimal routes to things. Centrality, all about looking at what's the most important function or important node within your network. It could be a bridge, it might be something with the most influence, and then community detection as well, often used in AI machine learning as well, to try to think how do things clump together and how alike or dissimilar they are. We've added quite a few of similarity algorithms as well. We've got an ebook available online with those, and then early next year we'll be coming out with a graph algorithms book with O'Reilly as well. So
the last thing I'll add on that is this is something that we're consistently looking to expand, to improve, whether that means you're looking at running an algorithm and you need help doing that, or you're looking for a new algorithm that you believe should be supported in the graph. We really need that customer and user feedback to understand what your priorities are. So please reach out to us to both understand how to better leverage these algorithms, but also to help us prioritize what algorithms come next as we continuously release new ones. So Amy talked a bit about one type of context in AI, but there's many types of context, right? We were looking at what are the contextual predictive relationships you have that might help you classify or predict a next action. And I want to talk about the contextual way in which you make decisions, in which people actually think, right? Hillary this morning talked about how neural networks are an incorrect approximation of how the human brain thinks, but it's not always really understanding exactly how neuroscience works. It's using them as a pointer to how can we speed up and optimize our own workflows. So one example that I was thinking about for this is, I don't know if there's many comedy fans in the audience, but when I think of Steve Carell, I think of lamps. And if you're a fan of Anchorman, if you're chuckling, it's, Brick loves lamp. And if you haven't seen Anchorman and you think I'm insane, I promise you should go check that out. But that's a relationship. But if someone asked me to do something a bit more intensive, and they said, who does Steve Carell remind you of? I'm not going to run that k-nearest neighbor classifier of Steve Carell against lamps and against chairs and against abstract concepts, right? I'm going to go through a process of filtration to think of, OK, let me think of what are the attributes that they share to narrow down, narrow down, narrow down, and then I'll run the more computationally intensive aspect there. So I'm going to obviously start with people, right? I'm then going to move into he's a male. I might look at complexion. I might look at non-physical features. He's an actor. He's a comedian. And where I'm probably going to get is, if you've never noticed this, Steve Carell looks a lot like Ben Stiller. But I didn't just do this in a brute force algorithm of let me look at every image I've ever seen and every other image. And that's actually fairly close to how modern neural networks do computer vision algorithms. They're going through, and each layer is looking at, even though it's not generally a human understandable concept, it's looking at filtering down. The machine learning algorithms that a lot of you are putting in practice in your enterprises, though, are not always as intelligent. And sometimes the filtration process that you're going through is really inefficient. So we want to talk about ways in which the graph actually helps you speed some of these up and get into production faster. And speaking of getting into production faster, Databricks and IDG had a study come out earlier this year about what the biggest roadblocks to scaling AI in the enterprise are. Oh, my phone
Your
wants to
phone's
talk
talking
to me.
to you.
Yeah. And one of the things really surprised me. It's one of the things I've seen. Gartner had another study that said 55% of enterprises are piloting AI this year. Only 5% have something in production. Databricks came out and said only 1 of 3 AI POCs are making it into production. And when they looked at what the biggest complaints were, tied for first was the time it takes to iteratively train a model. And data science is an iterative process, right? The more times you can try and tweak something, the better it's going to get. That's basically a rule. What really shocks me about this is it was tied with not enough data. If you either are a data scientist or work with one, we complain way too much about the data not being good enough, right? It's the consistent complaint. But one of the actual biggest problems as well is just how much time it's taking to work through these iterations and to train well. A lot of that is because you're not taking really efficient processes at heart. We're doing what Hillary did when she held up the tiny chip, right? To Amy's point, neural networks have been around for 60 years. Why have they taken off in the last 10 years? Mostly because GPUs have started to be leveraged for highly parallel applications. You're waiting for more hardware. Before Neo4j, I worked at Intel. We loved everyone waiting for more hardware. But there's more to optimization than what's the next CUDA release, right? And there's definitely more to optimizing your machine learning than renting more CUDA clusters on AWS, right? Start thinking about where are the inefficiencies in my model. When I think about why Neo4j exists, how we got started, I think the general problem statement was we exist to solve the computational inefficiency of connected data, right, of relationships. And what's the most common way relationships manifest themselves? It's in table joins. So if you get nothing else from me and every other talk here, I just want it to be table joins, table joins, table joins, table joins. They're terrible. Stop doing them. Right? They're great if you're just exploring data. But if you're building an application, you should be looking at a graph if table joins are your bottleneck. But they're not the only bottleneck. So obviously, if you're seeing them as you're bringing in data, but what are some of the ways that that inefficiency manifests itself in data science? One of them is what Emil talked about this morning, sparse matrices. If you look at some fairly common and well-understood machine learning practices, we talk about collaborative filtering a decent amount, that's really a giant sparse matrix, right? I'm a power user of Amazon. Maybe I bought 1 million products. Well, they have 1 billion. So at a high level, the matrix that represents Jake is 999 million null values and 1 million positive values. And obviously, there's ways that you can chop that down. But no matter what you do, those zeros have cost. And compressing them, because there are definitely sparse matrix compression methods, those are just more tables. They're more indices. They're more lookups. They're more complexity in your model. Graphs don't have null values. We just have the dot values. We just have the relationship values. So where you see yourself spending a lot of time compressing matrices, that's another place you can start thinking, I might have a graph problem. When you start seeing directionality, right? Multiple directions, multiple hops, but not just one linear direction, not just that tensor, but where you have multiple paths. There's a reason so many logistics companies use us, right? Graphs are able, we have directional relationships. When you start seeing you're getting bogged down with so many different trees, so many different, basically, multi-dimensional matrices to track these directions, you might have a graph problem. And then finally, the one I want to talk about a little bit more, is closer to the brick loves lamp example, is brute force. There are lots. So brute force is just the concept of I am going to run this calculation against all of the data that I have. Or I'm going to do some manual subsetting. Or I'm going to do in some kind of Bayesian inference to try and subset it. What those processes generally have in common is they're fairly manual. They generally require a data scientist to put in practice. And they're slowing down your iterations. Why? Why is it so hard? When in reality, what you can look at is clustering based on relationships, right? If I'm looking at a KNN, if I'm looking at classifying something via similarity, I can probably just look at anyone that has any shared attribute. Or how about anyone that has a shared attribute of someone I know or someone they know, right? In a graph, the query to say, return me a subgraph of only people that share any attribute that I have is trivial. It's milliseconds. And what you can do, if you take this visual PowerPoint example of a recommendation graph, and you can imagine that this graph might expand out into infinity, instead of running whatever classifier I'm running against all of those nodes, I can close to immediately project a subgraph. I can do it in an automated fashion. I can do it sometimes it's better to just do it in the dumbest fashion possible. I can look for specific features. I can use graph algorithms to tell me what features to run against. But what I can do is use it in real time consistently. And then from there, I can run my classifier to set up those weighted relationships of whatever I'm looking at, right? Whether it's a classifier, whether it's a regression, but only compare things against things that are likely to have anything to do with them, right? The graph helps you speed up that pipeline. So I want to move on to, so yeah, just coming back through, just to think through what you see that you might have a graph problem in an inefficient data science workload. Table joins, I'm always tempted to just get up and just try to lead a table joins chant, stop doing them. But also sparse matrices, directional problems, and brute force, it's really as inelegant as it sounds, right? You should stop doing it. So moving on to how we're creating the context for decisions that Amy was talking about. One of the AI spaces and data science spaces that's moving into production the fastest is decision support. Right? It's where you're taking a human decision that requires that person to have the right contextual relevant information and trying to automate it in some way. Now, there's lots of things that you can automate out that are mundane tasks, but that still leaves you with the hard tasks. And generally, hard tasks are solved today by domain knowledge, right? You just train more experts. You just build up more experience so that someone can say, I've seen this problem before, I remember it. There's really no reason for that to be the case anymore. And really what we're talking about is knowledge graphs. And I want to at least try to define knowledge graphs, how I define them. It's a term that gets thrown around a lot. I think of knowledge graphs as a connected, dynamic, and understandable repository of different data types. So pulling that apart quickly, it needs to be connected. It is not a data lake, right? It needs to be connected around the attributes that are actually relevant to this knowledge. Data is not knowledge, right? Not all data is knowledge. You're looking for relevant information that's connected on contextual lines. It's dynamic in that the graph itself understands what connects these things, right? It's not looking at, you need to go through and manually program every new knowledge piece that comes in. It's able to make those associations across the attributes that are important to you because you've already programmed that in. And it's understandable. Sometimes you say it's semantic. The knowledge tells you what it is. There is intelligent metadata associated with it so that you can traverse this graph to find what you need to answer this specific problem, even if you don't know exactly how to ask for it. In general, in different data types, I generally tend to define knowledge graphs as it needs to be heterogeneous. It's not just you have all of the same data type in here. In general, there's ways that graphs can help you with that, but I wouldn't call that a knowledge graph. We need to be looking at multiple different types of data. And the last part of the definition, a knowledge base is not a knowledge graph. Right? Having everything in a data lake is a fantastic thing. You need it to get started. But if you can't figure out what something is and where it is and how it's connected to other things, that is not a graph. So instead of talking about one example, since I think we really are the de facto leader in this space, most of the most common knowledge graphs people talk about, other than the Google knowledge graph, are built in Neo. Instead of giving one example, I want to talk about the three major types of knowledge graphs that we see in the market. And these aren't Neo4j canon terms. These are just my terms. So you might see them slightly different. But I tend to think of these three types of knowledge graphs of context-rich search, external insight sensing, and enterprise NLP. I like to think of them as basically a hierarchy. The first one we're going to talk about is the hierarchy of your data types. What are the types of knowledge you're looking for? What are the types of documents that we're trying to traverse? The next level I tend to think of as what are the entities? What are the things, the specific objects that we know are important, and what's all the information that's being generated around them, and how can we generate insights from that in a non-prescriptive way? And then the last one is getting into the actual granular level of your language. It's the biggest problem in scaling NLP in most enterprises is that you're not talking about natural language. Right? The natural language part, there's a long way to go, but that's a fairly well-solved problem. Google is not helping you to find your own ontology, right? Your technical terms, your product names, your product families, your industry acronyms, your synonyms, your common misspellings of those technical things, your part numbers. These are all technical terms that are custom to you. They're enterprise language. Where we can step in is to help you map those together and build that ontology. So just giving a little more info on each. Context-rich search doesn't actually just have to be search, but if you are looking at just doing TF-IDF, term frequency, inverse document frequency, if you're just doing keyword document search across large corpuses of heterogeneous knowledge, you've probably found it doesn't work that well. What a knowledge graph can allow you to do is understand the context and how things are related and traverse that much faster. But there's non-search applications as well. We've seen them used in customer support. If you're in an enterprise where you get tens or hundreds of thousands or more complex technical support issues a year, being able to show a technical support person what's the most similar problem we've ever seen, how was it solved, and what are the associated knowledge documents and technical documents to this problem can accelerate resolution enormously. Where I tend to talk to people about looking for context-rich search, identify a process in your enterprise that you know is inefficient. Measure that inefficiency and build a knowledge graph and make sure that you're actually targeting moving that KPI up. Right? Building KPIs in around AI workloads is critical. So look for that inefficient knowledge worker process and start asking the question, what do you need to answer this question better, and build that into your graph. External insight sensing is generally where we see this is when you're combining internally known entities and the knowledge around them with external information. So we see it in things like supply chain risk, right? The ability to look at all of your suppliers, all of the places they have manufacturing, all of your supply lines, and associate those with disruption risk. Being able to tell that your competitor is being tweeted about buying one of your suppliers and flagging that information. Being able to look at a natural disaster is hitting a specific place that you have a supply chain and giving someone options or what are similar suppliers that you have. Or looking at market opportunities, looking at financial information, looking at investment management or investment banking, being able to understand what are the types of companies, who's talking about buying who, so that you know who you should be talking to, who you should be targeting in your CRM to go sell services. But in general, you're looking at, there's an enormous amount of information in the market. We need to be able to sense it, determine what's contextually relevant, and present it to the right person. And then finally, enterprise NLP. I already jumped ahead of myself and talked about how we can help build. Hillary Mason this morning talked about word embeddings. There are lots of fantastic word embeddings libraries. All the CSPs are getting better. They're probably not doing it for your business. They are using graphs to build them, so should you. And then the last one I want to talk about is a bit more on the research side. It's another thing that was talked about this morning, explainability. And it was kind of funny at the graph talk, one of the ways she didn't talk about adding explainability to neural networks is actually there's a lot of research going around graphs, and specifically graph databases, to start to bring that explainability to complex neural networks. And I do think it's important to recognize when we're talking about explainability, we are talking about deep learning. In general, even complex decision trees, if you get into a large random forest, their outputs are still individual layers. You can still see feature and coefficient, right? It might not be business analyst readable, but you can get to an explanation. Complex neural networks are not explainable to the data scientist who wrote them. So I want to give an example of that. There was an interesting example last year in an academic setting of a professor who asked his class to build a classifier for photos of wolves versus dogs. And that's a very hard problem, right? Those are actually pretty similar. Even though it's a snarling wolf and an adorable Vizsla puppy, it's a pretty hard thing to be able to identify. One student actually did a really good job, though. And he was getting really good values on labeling things as a wolf versus a dog. And no one else had been able to do this. And the professor was trying to understand, how did this happen? So one of the methods that people use to bring explainability is called perturbing the model. You're going to take in a known data set, you're going to feed it in, and you're going to see how your classifier reacts to that data set to try and abstract, OK, I changed this specific feature. I can see where this is going. It's a pretty cumbersome process. But he was able to perturb it and find pretty quickly what was going on. Fed in not this exact image of an adorable puppy helping his owner clear the driveway, but something similar. And what they found was every time that came out, it was coming out as a wolf. Give me my stamp. There it is. And then in whatever dystopian bureaucracy that you can imagine that the algorithm says to do this wolf would then happen to this adorable puppy. And what he realized was really similar to what Hillary was talking about this morning. So French fries near the water, snow and a dog equals a wolf. That's obviously not right, but in order to understand that, you had to feed through known data sets, figure out where the problems were, manually go through and look at these, go back and piece it apart. And this is a professor of computer vision, right? This is, if you start thinking about, we all talk about these all the time, right? Healthcare, credit risk scoring, approvals, crime detection, sentencing, like the list goes on for the things that people want to apply deep learning to. If you can't tell that this puppy is not a wolf, you probably shouldn't be recommending sentencing yet. So what are the different types? And it's important to break these problems down into the type of problem we're talking about, right? It's not just explainability for all AI, because not all AI is inexplicable, right? It's deep learning. Within deep learning, what are the types of explainability we're talking about? Well, there's explainable data. What data did we use, right? Can we even understand how this was trained? That can actually be a lot harder than you think if you start talking about some of the major cloud service providers telling you what data Facebook has used exactly to get to all of its algorithms. It's actually not that easy of a problem. Explainable predictions. That's where we're talking about things like perturbing the model, where you're looking at the algorithm itself isn't explainable, but I want to understand specifically why it's giving me this value. Let me try to piece this apart. And then the panacea, explainable algorithms. So algorithms where you can actually get those coefficients out. And the important part of this one is those already exist in deep learning. They're just not performant. And we already talked about how hard it is to get more GPUs and how great NVIDIA's stock price is doing right now. Performance matters. So limiting performance is probably going to be a non-starter as well. So how are graphs starting to be looked at in this space? Explainable data is an easy one for us. We have 20 of the top 25 financial institutions using us in some way. Data lineage is a pretty common way, right? The ability to understand how data was changed, where it was used, why it was used, who used it, is something that we can do really well. If you're pulling that data in from a knowledge graph, it can also tell you what that data is, right? It's explainable. It's got semantic understanding. So that's low-hanging fruit. Explainable predictions. There's something cool that's come out very recently. A partner of ours, Fujitsu's AI Labs. This photo is actually from some of their public information. If you search for deep tensor and explainable AI, they're using knowledge graphs to help get to explanations for specific predictions. So this particular case is taking genetic mutations and looking at them to try to associate them to specific diseases in ways that haven't been done before. And when you're combining hundreds of thousands of mutations with equal amount of diseases and multiple layers of classifier, that's very difficult to do, except what they did is they built a knowledge graph that included each one of those mutations, included those diseases, and it also included all of the academic information that describe those diseases, that talk about them. And they set up that semantic connection around, look for mutations, look for diseases, look for the things we're looking at. And what happens is you can still see the neurons, in this case the nodes that are used in a neural network. What you can't tell is how they were used. But if you can see which nodes were actually used in a prediction, you can then traverse your knowledge graph to say, oh, well, this makes sense. I see that this research paper is associated with this research paper, and actually I can see that this genetic mutation is being talked about in something similar. Right? So it's still not very elegant, but it is more elegant than just trying to feed in more data to perturb your model, because you don't have the photos of more dogs to feed in that are labeled for this, right? You're looking at unknown patterns. If you don't have known patterns to perturb that model, it can be close to impossible to do that. So the knowledge graph is allowing researchers to say, these mutations are associated with these diseases, and here's all the documentation that abstracts it why. And then finally, we get into explainable algorithms. This is a bit further out. We are starting to see research, and Fujitsu is actually working in this as well, of actually constructing your tensor in the graph, making sure that linear relationship is actually weighted relationships between nodes, which is showing signs of being able to actually get at the explanations and the coefficients at each layer. But I don't want to overpromise that too much, because I actually haven't seen it working yet. But that is some of the cool, fun, and exciting stuff that we're working on right now. So with that, I am going to pass it back to Amy to close us out.
Thank you. So I think by now you've hopefully understood the theme is context for AI. And in particular, to just remind you that aggregation of information is not intelligence, nor is learning without context. That's not intelligence and comprehension. So think about what you're doing, and if you're still asking yourself, will graphs help me? Will graphs help my AI or my machine learning? They're pretty much 4 areas. I think we covered them, but just quickly to summarize is look at your model. Do you have predictive relationships or network components that are predictive that you can't reach? You've got to 2 hops, but you're trying to get to 3 or 4 hops out, and look for those indirect inferences and connections. Are you, dealing with a lot of joins? I think we talked a lot about, we think we've flogged that. Yes, no joins. Joins are bad. But also if you have a lot of sparse matrices or other highly indexed components in your model. Also directional, we talked a little bit about that. That is such a classic graph application, is understanding paths and understanding direction and how things spread through a network. And of course, the knowledge sources, if you've got a lot of heterogeneous knowledge sources and stories over, or sources all over that are hard to integrate, that would be another indication as well. So with that, if you guys have what we really need for you, so we want to help and we want to work together on new solutions, but what we really need from you guys is come tell us what algorithms aren't in the library that you want, and come tell us how we should integrate with the workflows that you have. So thank you, everybody. Come find us afterwards for questions.